Okay, well, welcome back, folks. I apologize for yesterday. I'm not quite sure what happened to the video, so I'm going to go ahead and re-record the video today. And so hopefully you folks had a good weekend. I want to continue on with this discussion of kinematics. Depending on what the situation is after spring break, after Easter break. So tomorrow will be our last day before Easter break. Depending on what the situation is, whether we continue on with this online remote learning or we actually are able to go back to school. I'll let you know about the exam situation moving forward. And so, but my hope is that somehow, if it's possible, we'll get back, meet in school, and then we can continue on with our build with the programming. So let's keep our fingers crossed. Let's see what happens. But I'll let you know when we get back from Easter vacation what the situation is going to be. And I think we will all find out by that time. Okay, so with that said, then we're going to continue on as if we will be doing the remote learning here. And we left off with the kinematics. We were talking about then how we can calculate for, we can use the formula for velocity. And remember, what we're trying to do here with this particular this problem is we're trying to describe a phenomenon. The phenomenon we're describing here is the change in position. And so that change in position is defined then as, and if that change in position involves the direction, as the velocity, okay? And we are able to obtain this formula for the velocity, which is the how fast something is moving and its direction by plotting the position versus time. And we saw that the slope for this particular phenomenon known as velocity, okay, is the change, is the rise of the run, which is the change in position over change in time, which is then going to be final position minus initial position all over t final minus t initial. And so this equation here we can use to help us predict different aspects of the motion. For example, if you know how fast something is moving, we can figure out how far it's moving if we know the time interval. Or if we know how fast something's moving, and we know how far it moved, you can figure out how long it took to cover that distance. And then finally, if we know how far it moved and we know the time interval, we can predict its speed at a certain moment in time, what we refer to as the instantaneous velocity. And we saw then we can calculate for that instantaneous velocity using a little bit of calculus, using limits here if we need to, or we can just simply take the position time graph, excuse me, take the position time graph and then find the line that is tangent, the slope of a line that is tangent to a point on that position time graph, and we have the instantaneous velocity. And the instantaneous velocity is the speed at which an object is moving at one moment in time. That you have to keep in mind and remember that definition, because we will use that definition in just a moment of what is an instantaneous velocity to describe another phenomenon of motion, which we refer to as acceleration. Okay, so this is how we define velocity. This is the formula that we use to define velocity. And from this formula, then we can use it to predict different aspects of the motion relating to the speed of an object and its direction. Okay? And so with that said, then I asked you to finish up this problem on Friday. And so let's go ahead and work this out here. And what you want to make sure you do when you work out these problems is you want to make sure then that you identify what is given to you. Okay, and let's go ahead and do so. So we are told here that we have a car that's moving at a rate of 55 kilometers per hour. Hopefully you recognize then that the unit here, kilometer per hour, describes speed. We are given a time here of 0.75 seconds. Okay, that would be your time interval. And so they're asking us to find then how far the object moves, okay, how far this object moves at this particular, in this particular problem. So go ahead then, let's go ahead and use this information solve for this particular problem. Let's go ahead then, and I'm going to go and let's go ahead and work through this particular problem here. Okay. All right, so let's go ahead and let's write down what we're given, and let's work this one out. Okay. I would always suggest that you draw a picture here, and I thought it's going to be important that you draw the picture to help you. But again, the formula that we're going to use then is going to be the formula for velocity. Remember, speed, then I would leave out this line here because speed is a scalar quantity. Velocity is a vector quantity. The difference between scalar and vector, Scalar has only magnitude. Vector has both magnitude and direction. All right, so from now on, I'm going to be writing time interval here, not as a change in time interval, but just as t. T typically represents the change in time or the time interval. We rarely deal with a single moment in time. Like I said, even though we will talk about that with acceleration, but when we talk about the change in time, remember, it's always going to be t final minus t initial, and I'll abbreviate that now as t. Okay? All right, so this is what we'll be using. This is the formula that we'll be using to get this done. Already, like I told you in the previous example, we were able to describe the velocity here as being 55 kilometers, and I'm going to write this kilometers per hour. This is a unit ratio, meaning then that's 55 kilometers for every 1 hour. And remember, please make sure you keep in mind that all of the ratios that we'll be dealing with here, for the most part, will be unit ratios, which means then it's going to be some quantity over another quantity, but over one. Okay. All right, so with that said, then we are also told that we have a time interval of 0.75 seconds. So t then, it's going to be 0.75 seconds. And we are asked to find then how far the object acting was. So we're solving for delta x here. Okay, and so with that said, then rearrange this formula here to get the equation that you'll need to solve for delta x. And this is a practice that I would suggest that if you haven't been taught that yet in physics, but I think Mr. Sansalone does a good job of doing this here, or if you have not taken physics yet, what I would suggest you do then is when you are asked to find a particular solve for a particular problem, make sure then that you set up the equations that your unknown is on one side and what you know is on the other side. So basically, we will be solving this formula here for delta x. So with that said, then we'll multiply both sides by t. So that's the formula that we're going to be using to solve for this one, okay? All right, so with that said, then we have our velocity here, we have our time. It seems like we can plug it straight in, but be careful here, folks. Okay? The units of time here don't match up. So what we have to do is we have to convert this unit of time and the unit of distance here into the appropriate units, okay? And so with conversions, then essentially what we are doing with conversions, and if you have a question about how we do these conversions here, please make sure you come by and see me after school, right after the lecture today, and we'll talk about it. But basically what we're doing with conversions here, we will be changing these units here into different units, okay? And we want to change it into units of meters per second, okay? And so therefore, we need then, if we remember, the relationship between kilometers and meters. It's going to be 1,000 for every 1 kilometer, 1,000 to 1. And so why do we do it this way? Is because in fractions, remember, in ratios, if the units appear on both sides of that line, so if it's in the numerator and the denominator, it cancels out. So we want to get rid of this unit here. And so we end up with units of meters on both sides of the arrow. And then finally, we want time here to be in seconds. So therefore, we got to make sure then that we define the relationship between hours and seconds, which is 3,600 seconds for every 1 hour. Now, if you don't remember that, I think that's a fairly easy number to remember. But if you don't remember that, you can also convert between minutes to minutes first and then to seconds. Okay, so again, folks, with that said, if you are not familiar with how to do these fairly simple conversions, come by and see me, and then we'll go over. Okay, so make sure you come by. So with that said, then, this ends up being 15.3 meters per second. Okay, so that's the velocity in meters per second. This is how fast the velocity of the object, the car is moving in kilometers per hour. These two rates are exactly equal to one another. It's just we are expressing it differently. That's the whole idea behind conversion. Why do we have to convert this rate, this velocity to this rate here? Because again, the unit of time here is seconds. We need to make sure that this unit of time here is also in seconds. Okay? And then could we have kept the kilometers in there? Sure. But we've learned and we have been using meters per second as the unit for velocity. So I just went ahead and converted the length unit, the distance unit, the length unit as well into meters. Okay? So again, please make sure, if you're not quite sure how we got those and how we plugged it in, come by and see me. All right, so now that we have that, then let's go ahead and plug in our velocity, the converted form of 15.3. This real quickly. Okay, 15.3 meters per second, okay? And we're going to multiply that by the time interval of 0.75 seconds, okay? And there it is. This is the reason why we need that the unit of time there to be in seconds. Just the unit of second cancels out. And then we end up with a length unit, which is what we need here for displacement. Okay, so when we plug that in, we end up with our answer then as being 11 meters. And that is how far the car moves as it slows down the 0.75 seconds. So it'll move 11 meters. So understand this, what this is telling us is then the car will take 0.75 seconds to start its deceleration, and I'll talk about that term in just a moment. But it'll take 0.75 seconds. But before that's the time interval. But the distance it travels before it starts to slow down is going to be 11 meters, and that's what this answer here gives us. Okay. All right. So with that said, that's how we use the formula for velocity in order to calculate then for here, in this case, displacement. Okay. Please make sure you understand that. Okay. Because what you need to make sure you also understand here is this. Okay. So let's go ahead and let's write out this formula again. So the velocity is going to be the change in position over the time interval, which remember delta x here is x final minus x initial all over the change in time. Let's say we didn't want to find out the total distance it's traveled here, but we want to find out where it actually ends up. If we know where it starts out at, we can find this. We can find that final position by a simple rearrangement of the equation. So what I would like you to do now is I want you to rearrange this equation here. And this is just a little bit of algebra to help you practice this, okay? Rearrange this equation here to solve for x final. Okay, so I'm going to pause the video here just a moment on your paper, and this is practice for you. I want you to solve this equation here for x sub f, which is the final position. Okay, go ahead and write that on your paper. You will not have to include this on the ed puzzle itself. It'd be difficult for you to do so, but make sure you write it on your paper, okay? And then you'll submit that at the end of this video. So go ahead, take about a couple of minutes, or actually a minute, to solve for x sub f. Okay, and then I'll go over it with you when you get back. Okay, go ahead, get it done. Okay, hopefully you got this done. Okay, so we're going to solve for x sub f. So I'm going to go ahead and erase this here first. So let's do it a step at a time. Okay, so go ahead, erase this. So if we're going to solve for x sub f, which is the final position, we got to isolate x sub f all by itself. So if you notice here, we got t on the bottom here. We got to get rid of that first. So in order to get rid of t, we're going to multiply both sides by t. Okay, we multiply both sides by time. This cancels out over here. We end up then with v sub t, v times t on the left, x f minus x 0, x naught on the right-hand side. Okay. All right. So we need to isolate x sub f all by itself. So what do? We're going to add x sub 0 to both sides. Okay. So add x sub 0 to both sides, and then we get here then x sub f on the right-hand side, and then we have then x naught plus vt on the left-hand side. And so just to write this out in the format that we were more familiar with, then I'm going to write this on the left, which means then it's going to be vt plus x naught, and that is how we would solve for x sub f. Okay. So if we know, to understand this, what we did was we took what we know about the velocity. We took this formula here, and now we can use it to find the final position of an object if we know its initial position, if we know its speed or velocity and its time. We can also use, and I'll leave it up to you to solve for this here, we can also calculate for where it started out at, its initial position, if, again, we know this x final, which is the final position, if we know its velocity, and if we know the time interval at which it traveled. So the whole idea behind these formulas then, folks, that we can use these formulas to make predictions like this. Okay? Using simple algebra, using simple math, we can make these predictions. And this is why in physics, we want to be able to describe motion and all physical phenomenon in terms of equations. Now, obviously, as we move forward, and those of you who are taking physics now, you've already seen, as we move forward, the equations become a little bit more complex and the math becomes a little bit more complex, but the idea here is still the same, okay? So I want you to keep this in mind as we move forward, and we talk about acceleration in the next unit, but that's what that's what we'll be doing, okay? So very good. Hopefully you have this written down. Okay? And so let's go ahead and so there it is. So what I've done for you here is I've described for you how we can find the final position of, that's how far it moves, the final position, if we know the velocity, the time, and its initial position. All I did here was change up the variables, but what we end up with is exactly the same. Okay. Okay, so let's go ahead then, and that finishes up the first part of our kinematics unit. Okay, so we know now how to represent motion. We talked about we can draw diagrams, we can draw particle, we can simplify the diagrams into particle representations. We can plot the motion on a position time graph and explain them from there, the position versus time. We use that position time graph also to define the velocity, and from there we were able to obtain the equation, the formula that describes velocity. And so we were able to represent motion at the end of, at this point here, we can represent motion in terms of an object's position, in terms of the object's, how long it has moved, and also its speed. And then that speed then is the ratio, a comparison between how far it's moved, its position, and the time interval itself, okay? So in our study of kinematics so far, in our study of motion so far, we've been talking about an object moving in one direction, in one dimension, at constant speed. But we know then in real life that objects do not move at a constant speed, that the objects in real life speed up and they slow down, okay? And they make turns. So what we're going to do then as we continue forward is we're going to talk about then this speeding up or slowing down, which is called accelerated motion, okay? And how we define that. And then what we'll do in part 3, hopefully, is we'll talk about two-dimensional motion a little bit more. But right now, we're still talking about an object moving along a single line, one-dimensional motion. But this time, what we're going to be talking about, what we will include into our description of motion here, is an object that is going to be speeding up or slowing down. Okay? And so as an object speeds up or slows down, okay, make sure you keep this in mind then, its velocity changes, its speed changes. So when an object accelerates, its speed will change. And so I had used that term deceleration, and I don't really like to use that term deceleration because acceleration applies to both an object that's speeding up and slowing down. Because acceleration in physics is described then as a change in the velocity velocity with a given direction. So therefore, acceleration is also a vector quantity, and we'll talk about that again in just a moment. But make sure you keep this in mind then, that what we're going to be doing is we will be defining the acceleration as the change in the velocity over a given time interval. Okay, so you're going to see then that the equation that we will come up with will be very, very similar to what we had used in the previous section for velocity. Okay, so what we want to be able to do then is we're going to be able to solve the problems involving acceleration. Now this time though, acceleration is constant, meaning then that the object is continually speeding up or continually slowing down. When we say constant acceleration, make sure you keep this in mind, folks, and I want to emphasize this here. Okay? When we talk about constant acceleration, we are not talking about an object moving at a constant speed. That was in the previous section. In the previous section, we talked about constant velocity. And this is something that a lot of first-time physics students have a very hard time with, and that is constant velocity means then that the object is not accelerating. It has zero acceleration, but it's moving at a constant velocity. This is something that I will emphasize as we go through this particular section here, but do make sure you keep this in mind, okay? And so we're still talking about one directional motion, okay? Object moving in one direction, but at constant acceleration, okay? And so what we're gonna do then is at the end, so here I'm gonna reverse things just a little bit. We'll talk about the equation first, and then we'll talk about how we can graphically obtain that acceleration. We'll talk about velocity time graphs, okay, towards the end of this section. And we're going to examine velocity time graphs and see then how the velocity time graphs will give us the equation that I will introduce to you first. Okay, so in this particular section, I'm going to reverse things just a little bit. We're going to talk about the equation, the formula first, and then we'll talk about how we can obtain that formula from the graph. Okay? All right, so let's go ahead and let's talk about acceleration. Then let's take a look at what that means. Okay. Okay. So acceleration can occur whenever an object changes its movement, changes its speed. Okay, but make sure you keep this in mind that when we talk about acceleration, an object can also change its direction. So it either can change its speed or change its direction. We're going to leave out the discussion of changes in direction right now because we're still only talking about one-dimensional motion. But in the last section of this unit here, we will talk about changes in direction as also being an acceleration. Okay, so if you look at these race cars, these race cars here, these Formula One cars here, as they go through this curve here, they will be changing their direction. As they move out of the curve, they will start speeding up. So as they move through the curve and as they speed up, they are accelerating. But make sure you keep this in mind that as they come into the curve, they have to slow down. As they come into the curve, they have to slow down. That also will be defined as an acceleration because they are changing their speed. Okay, so make sure you keep that in mind. Okay. All right, so with that said then, let me go ahead and finish up these videos real quickly. So we can solve for a lot of these problems using a very simple equation, okay, using a very simple equation. And so using that simple equation, we can rearrange it very much like we did a couple of slides back where I asked you to rearrange the equation for velocity. We can do the same thing for the definition, for the basic definition for acceleration. We can do the same thing and obtain different equations that we can use. Essentially 3 different equations that we can use, which are called the kinematic equations. And from those kinematic equations, we can make predictions about velocity, about displacement, about position, and for an object if we know the other components of how that object moves. Okay, so we'll talk about these kinematic equations and we'll talk about how we use those as well as we progress through this particular section here. Okay, and then finally, then what we're going to do is we're going to discuss then a specific type of one-dimensional motion in constant with constant acceleration, and that is what we call a free fall. A free-falling object undergoes constant acceleration. That acceleration is gravitational acceleration, which I think many of you would know. Many of you probably have heard of before, which is that 9.8 meters per second squared. And that is the acceleration caused by an object falling down towards the Earth, falling down towards the surface of the Earth. And the reason for that is because the Earth is pulling down on every object with a constant gravitational force. Okay, so with that said then, that's what we will be doing in this particular section. We'll continue this tomorrow and we'll get through the first discussion and first calculation involving this equation here. So we will be focusing our attention, and what we'll be doing tomorrow, we'll be focusing our attention on this equation here and how we can use that to describe acceleration and how that acceleration is related to velocity changes. And these velocities here will be instantaneous velocities. Okay, so we'll define that as well. And how that change of velocity is related to the change in time. Okay, so we're going to focus in on this equation here, on this formula here tomorrow. And then, like I said, I'll show you how this particular formula is going to be obtained from a velocity time graph, and we'll talk about that hopefully after Easter break. Okay. All right, very good, folks. So I will see you tomorrow on Classroom here. Stop by and stick around, or stop by after school today, after you watch the lecture here, if you have any questions on the material here. Okay. If not, I will see you folks tomorrow.